delighted to have medical physicist Bryce Hamilton with Elizen Medical Physics with us to educate us on commissioning and implementation of portal dosimetry and the PDIP algorithm. Before I turn it over to Bryce, I will give you a moment to review the Varian safety statement. Bryce, take it away.
Thank you, Karen. Like Karen said, my name is Bryce Hamilton. I'm a physicist with Elizen Medical Physics. And hopefully at the end of this talk, we're going to have a better understanding of how to get portal dosimetry commissioned and implemented in your clinic, and a better understanding of the parameters in the PDIP algorithm. So first, let me begin by briefly discussing. I'm sorry. There we go. Let me begin by briefly going through some disclosures here. And everything I'm going to be discussing, I'll be talking about ARIA version 13, and I'll be using the TrueBeam. I will briefly talk about the C-series machines and some older panels, but most of the discussion at the end talking about custom implementation of a portal dosimetry algorithm will be using the newer TrueBeams with the new panels, and I have access to version 13 of ARIA, although this would be applicable for most versions as well. So let me talk very briefly about Elizen, the company that I work for. We are a physics service group. We provide service mostly in the Mid-South region, Arkansas, Missouri, Kansas, and Oklahoma. We have a few clinics, but mostly we provide commissioning through North and South America. And we have hopefully optimized a lot of those procedures of commissioning so that we can provide a lot of extra things like portal dosimetry. So the objective of this talk is we're going to begin by talking about the fundamental theories of portal dosimetry, how portal dosimetry very broadly does what it makes the calculations and gets an image. And then hopefully we'll be able to talk about the algorithm, the modeling, and understand all the parameters that go into this. I know that when looking at the algorithm itself, sometimes it's a little black box. And I think that by the end of this, we'll be able to look at those and find issues with the algorithm, find issues with images that you're taking, and maybe be able to tweak the algorithm to get a better solution. And then at the end, I want to talk about some of the pitfalls, some of the limitations, and discuss kind of where portal dosimetry is most useful, where it might not be as useful as maybe another device. So let's jump right in and talk about PDIP. PDIP is Varian's portal dose image prediction algorithm. Again, this is Varian provided. This is very different than maybe, say, the GLASS algorithm, something that has been published in the past. But this calculates portal dose directly from the Varian algorithm reference guide by convolving the fluents with Gaussian kernels. And provides this equation here where you get a portal dose, P, by taking a intensity profile corrected fluence. Now this is the fluence from the head of the machine, the calculated fluence determined by, in treatment planning, and convolving the corrected fluence by the intensity profile with the kernel, doing an SSD, SAD correction by the panel distance, and then applying some output and phantom scatter factors to that. But I want to be really, really careful about saying portal dose. We have to keep in mind that this is not technically dose. We're not using ion chambers. This is a diode array, and we have to calibrate this panel. And Varian has created this unit called calibrated units, or CU. And I want to just say that this is exactly the same thing as doing a cross-cal. So we should always know that anytime you calibrate your panel, you are calibrating in reference to the output of the machine. This is a direct cross-cal to your machine. So if your machine is delivering 5% hot, your panel is going to read 5% hot off that calibration. I don't want to, so that kind of gives us an overview of what portal dosimetry does. How does it kind of do its calculation? But what can we really use it for? Well, the obvious answer is patient-specific QA. We can use it for IMRT and RapidArc verification, or we can use it for field-in-field verification for breast patients, for example. Anything that the MLC moves, we can do a prediction and therefore take an image and get a comparison. But maybe a little less common knowledge that portal dosimetry can be used for is we can do physics checks with this. We could do any kind of baseline comparison. There's a set baseline tool in the portal dosimetry module that can be really useful to us. That we can do things like output checks, for example. We can verify flatness and symmetry once we set a baseline. We could do picket fence evaluation. I have a tendency to use the chair pattern, which I'll talk about pretty extensively later, to verify MLC motions and verify that some of my MLC parameters in the treatment planning system are still valid, maybe after some sort of PMI or repair by the service engineer. I find portal dosimetry to be extremely useful for those kinds of things. So just as an example of an IMRT QA, this is a RapidArc test plan delivered, and analysis is 2% 2 millimeters here, gamma analysis, and we can get some really useful information here. We can see things like what is the maximum gamma value, what's the average gamma of the evaluation. We can drag around the profile cursors and see where failing points are, if there were any. This is an extremely useful interface that gives us a lot of information, other than just does it pass or does it fail. Also, a way that I use this is we'll talk some about these, in particular, these fields later, but this is just an open field, a 10 by 10. I can look at this directly and I can see that the CU is constant, so my output is the same as what it was when I calibrated it. I can see that the profile looks symmetric. It looks like we're getting a good clean curve here. And this is compared to a predicted value, but there's no reason that I couldn't take this image and set a baseline by going in and using the tools that are available here and doing the same thing for picket fence tests. So you're getting a more qualitative estimation of a picket fence test as opposed to a quantitative view of a picket fence test as opposed to just kind of giving a qualitative, well, the MLCs look like they're moving correctly. Also, a really useful tool in the portal dosimetry application is the output factor tool. This tool, once you establish a baseline or establish some good clean values, we could really look at this and see our output factors. We could use this on an annual, for example, after we set baselines to establish that the output factors are still consistent. This would be a very, very quick way to take output factors. Those are just a few examples of how versatile this panel is and how it could be used pretty extensively. I'm going to talk quickly about the portal imager itself. As all of you, I'm sure, know, this is an amorphous silicon construction. To the right there, you're seeing just a very schematic view of what that's going to look like. It's not really the point of this, but let's talk about some of the options on these machines. Oftentimes, the early C-series machines had an AS500 or an AS502. You can look at that pixel resolution of 512 by 384, kind of a low resolution. What's really interesting about this panel is that you get a 40 by 32 in the X and Y respectively field of view, and that's when the imager is at 0. I say image vert at 0, meaning at ISO center, just to make a note that sometimes you're not going to be moving that to 0. Sometimes we're going to have that at an image vert equals -5 or 105 SSB. That typically, or that will make the field of view go down a little bit, obviously, and that field of view changes to about a 40 by 30 field of view. The acquisition rate is really important because this tells us we could saturate this panel. If we're delivering higher dose rates or lots of very open information, we could easily saturate the panel at 12 frames per second. So when they upgraded and they went to the AS1000, they made some pretty good improvements, like made the pixel resolution go up. The field of view is still the same, but note that the acquisition rate is much higher. So they're able to limit that saturation to a point. I should note that on neither of these panels are they really qualified to do the flattening filter free beams. They would definitely saturate at the very high dose rates. I haven't done as much testing with this, but you could extend the panel down to 140 SSD or 150 SSD, for example, and that would lower the dose rate at distance and lower that issue with saturation. But the big problem with both of these panels is you get some backscatter from the imager arm. This makes the response of the imager asymmetric, and I'll show you a little bit later about a pretty good example of why this is an issue, why we're going to see problems when we have backscatter, and that's going to create an over response closer to the gantry. But on the newer TrueBeams, newer Vital Beams in the edge, we're getting this new panel, this AS1200 panel. The big jump from this is there's a 43 by 43 field of view, so we can get the full field of view on here. That's a much higher pixel resolution, and the saturation at ISO center is also, you know, we can deliver so much more dose to it at a time. So reading there, we can deliver approximately 3,200 MU per minute, which noting that the 10FFF maximum dose rate is 2,400. So this allows us to do the flattening filter free beams. And they also solve the backscatter issues, making the imager response symmetric all the way around. So the general workflow of how we're going to commission this is, first thing we're going to do, no matter what the imager, is we're going to calibrate it. Calibration is going to include a flood field, it's going to include a dark field, and then we're going to calibrate for dose. Then we're going to measure the output factors, and we're going to measure a required test pattern that we talk about. Then we're going to develop the PDIP algorithm, and then we're going to verify the algorithm. In that verification, we're going to also evaluate DLG in transmission. In Eclipse, that you only have one DLG in transmission value per energy as of right now, and we're going to talk about how you can dial those in. And then once we get those dialed in, we're going to verify with IMRT and RapidArc test plans, and we'll talk about how that's done. So again, when we calibrate the imager panel, we're going to first take a dark field to establish background. We're going to take a flood field to get this uniform response. And then we're going to do an important beam profile correction. We're going to tell the panel what it should expect to see when it acquires some sort of image or requires dose. This is very similar to a profile correction on, say, a map check. If you were to deliver a 6FFF beam with a profile correction for a 6 standard beam, you would see it try to make that flat correction, and you would get an odd response. So we have to correct this for every energy and every different delivery mode, standard or FFF. And then lastly, we're going to do a dose calibration. For example, 100 monitored units equals 1 calibrated unit. So once we do that, we're going to, start building the algorithm. The algorithm requires a few things. It requires output factors. Those output factors I typically will measure from a 1x1 up to a 40x40 for the large panel. I try to measure up to the max field size just to give a full field of view. We're going to give it an intensity profile. We'll talk about where that intensity profile can come from. And then we have to give it the actual fluence. So we have to give it a fluence that corresponds to an image that has been acquired. This fluence comes from the database and from the calculation database, and we'll talk about how that gets imported. And then once all we're done, it's going to calculate a kernel, and that kernel is used for convolution. So just a look at the intensity profile. This intensity profile is a diagonal profile typically defined at Dmax. It's just the half scan here. You can pull this directly from the AAA algorithm, for example, or we could import our own. What's really important about this is whatever you use here needs to be the same as what you're going to put on your panel. And well, that'll make a little more sense later, but we want to tell the algorithm the same thing that we're telling the panel. So whatever in diagonal you use here, it's going to take this diagonal and it's going to sweep it radially, so you get a radially symmetric prediction. And you want to be able to tell the panel the same thing, and that's very important. Next is this is what your actual fluence in the algorithm is going to look like. Again, this comes directly from the treatment plan. This is an example of an actual fluence from the ADA profile or ADA plan, which is a test plan that Varian recommends use. This actual fluence is what comes directly out of the head of the machine, and from the actual fluence, we're going to apply a kernel or calculate a kernel to get an image. So we have an image that we've acquired of the ADA profile or ADA plan. It's going to take the actual fluence and it's going to determine a kernel that'll get us to the image from the actual fluence. So it's kind of the basis of how this algorithm is actually doing its calculation. And this is an example of what a good kernel is going to look like when you're all said and done. It's important that you get this nice decay, and in a few more slides I'll show you, we'll have a picture of what a bad kernel would look like. So I want to talk about, an older set of machines, maybe with an AS502 or an AS1000. It's often easier to use the pre-configured packages here. The reason for this is what we talked about the AS500 and the AS1000 having backscatter. The asymmetry of that panel makes it difficult to make a correction. Your corrections are not symmetric. If you make that symmetric correction, you're going to get a pretty dramatic over response up near the panel. And I also find that these pre-configured packages are do a pretty good job. Those are available for a wide array of energies: the 6, the 8, the 10, the 15. The 18 and the 25, and I've used it for all of those except for the 25, and I get good results on everything. The EPID calibrations for those are provided for the 100 SSD or the 105 SSD, whichever is your preference. And we should note that this requires Eclipse version 10. But this correction, and again, I just want to note that the correction for the imager arm is kind of built in here into the intensity profile and into the EPID calibration that goes on. So we don't have to account for that on our own, which could be quite difficult because it's not symmetric. Just a very quick run through of how that's going to be done. All your imager calibrations are done in AM maintenance, which is what you're used to doing. Be sure that when you do your flood and dark fields, you do it for each dose rate setting. You're going to be, and also you're going to be doing this in the integrated image. It's important to do it for each dose rate setting, just because when it sees a dose rate or sees a set dose rate, that's the one it's going to grab. If you set 300 and you don't have a calibration, you won't be able to take that image. be sure to drive your support arm up, obviously, to the position that you're going to be taking this data, and set your field size correspondingly. So in that same AM maintenance screen, under maintenance, there's a dosimetry cal selection. When you do this the first time, you're going to do the beam profile correction. This beam profile correction is from my variant, the one that's listed here, this CDP file. This CDP file, by the way, is a binary file, very difficult to write and read. But you're only going to do that profile correction the first time, and then we're going to do a dose cal, and that dose cal is 100 MU, 10 by 10 field size. There is an SSD correction. If you're at 100 SSD, you'll set your dose to 1, and your measured dose to 1. If you're at 105 SSD, you're going to do an SSD correction there. Your imager dose is going to be 0.907. And once you do that, you're ready to go. We'll import the corrected the models, whatever models you want, into Eclipse, and then we can start validation. I did want to go ahead and show what the imager arm backscatter could look like. In image A here, we're looking at a 10 by 10 field size, and you can see that the predicted image and the acquired image look very, very similar. And then we even jump up into the 15 by 15. It looks very similar, but if you look really close, you can see that the green acquired image is starting to get a little bit of an over response. But much more impressively is when we go to the 29 by 29, you can see that image over response, that backscatter, where the green profile, the measured, is really dramatically over higher due to the backscatter from the imager arm to the predicted. Another shortcoming that we talked about is image saturation. When you would typically think about image saturation, you would think about seeing something very flat. You'd have a curve coming, building up, and then a flat plateau, and then building back down to the other side. This is not really what we see because of the way that the imager in integrated image mode pulls dose. It'll collect a little bit and then pull the dose off of those diodes and then continue collecting. So this is an iterative process that is occurring all the time. And that means that saturation is going to be the sum of all the parts. So this is more what you would see. This is a rapid plan delivery on an AS502 delivered at 600 dose rate. And you can see that you have this kind of jagged over and under response. I know that this wasn't a limitation of the plan because I knew my DLG and my other parameters were correct, and when I dropped the dose rate down to 300, I got an excellent response. I apologize, I don't have an image of that, but I got almost perfect response here when I dropped the dose rate to 300 and limited that saturation issue. So I just wanted to show an image of one of the limitations of that AS500 panel, for example, and what you could see in that saturation limit. You're not going to see some plateaus. You're going to see just an overall under response. Now I really want to get to the meat of my presentation. Really, the stuff that I wanted to really dig into is custom modeling. But before I really get into that, I should mention that Varian does provide some pre-configured packages for the AS1000 on the TrueBeam. And that's in the installation and verification of the portal dosimetry pre-configured package for TrueBeam family of products, and that's all on my Varian. This is provided only for the 6 and the 10x flattened energies, and it's really, it's really only useful for the Millennium 120 and the AS1000 panel. This is not used for HDMLC. It's not used for the AS1200, and it doesn't have any of the FFF configuration in it. But we'll jump into custom modeling, and we'll talk about, with the AS1200, why we can do that. So we can do custom modeling for the AS1200 because it is symmetric. We got rid of that backscatter issue. We have a symmetric panel, so any kind of adjustment we make is uniform across the panel. It's radially symmetric. Anytime that intensity profile can be changed, it's changed radially, which is really, really useful, really important. The AS1200 is also, like I said before, available for FFF configuration. I should note that FFF portal dosimetry is only available on version 13 and newer. Version 11 did not support the 43 by 43 panel, and you have to be able to tell ARIA that you have that panel. These test plans that we're going to use for IMRT and RapidArc and even some of the MLC testing are available on my Varian. That's the PDC package. And HDMLC can be configured, but we don't have any test plans for that, so we'd have to figure out how we're going to develop those test plans. So I'm going to jump right in. I'm going to talk about, again, general workflow here. First things first, we're going to calibrate the panel. We're going to take a flood in a dark field. This is exactly like you would do for any kind of imaging calibration, NPVA calibration in service mode or Imager Cal. It's going to do a flood in a dark field and then get a pixel correction. But then we're going to do our beam profile correction and our dose normalization. So our beam profile correction, the screen's going to look like this. We're going to put these profiles somewhere we can navigate to. Typically, I'm going to put them on the shared iDrive, and I can navigate to that iDrive using the file navigator at the top. But I should note that this profile correction is not generic. It is not the same for every energy. If you can probably get away with it a little bit with the flat beams, but you'll get a better result if you use a custom one. We're going to build this profile correction from the intensity profile. You're going to want to use the intensity profile. I mentioned this before. You're going to use the intensity profile that you used in the portal dosimetry algorithm to in here. There are a couple ways we can do that. The best way that I've done this is by just recreating a DXX image file that's pulled out of portal dosimetry and then radially applying that intensity profile to an image. You could do this by acquiring an image and then re-importing it. I find that I don't get as good of results, but it's one option. You can do it that way. After we get the profile correction put in, we're going to do a dose normalization. This is exactly the same as before. It's a little easier because it's going to drive for you than the C-Series machines are. But one thing I'm going to make a note of is under the dosimetry there, we can change the reference dose. We can change the number of CU that are read here. It defaults that 100 monitor units is 1 CU, but you can change that to anything you want. You just need to make note of what it is, because when you put your output factors into the algorithm, that has to match whatever you calibrated. If you calibrated it at 1 CU for 100 monitor units, but your output factors are calibrated for 100, obviously you're going to see 100 times different, and it's going to look, you're basically not going to see any dose compared to your predicted, and very quickly catch your mistake. Once we get the panel done, the first thing we're going to want to do is we're going to want to measure output factors. This is directly, again, out of the algorithm guide. Output factors can be measured all the way up to the full field size. This jumps up to the 38 by 38, but there's no reason you can't do all the way to the 40 by 40 at 100 SSD. And I'll typically do this all the way down to a 1 by 1. I like to get full range of my panel, and I use portal dosimetry oftentimes as another verification of my SRS or SBRT plans, along with a point dose measurement or something like that. This plan I create manually in Eclipse. It's a pretty substantial undertaking, and you should note that delivery of this is going to be probably the biggest chunk of your time, just because you need to deliver this in treatment mode so you can get your images acquired. I then use the output factor tool provided in portal dosimetry, in the portal dosimetry workspace, and you'll see that in a little bit. The other thing that we need to deliver before we do anything else is the ADA test plan. Anywhere, the best way to do this is you've got to import an optimal fluence onto a field, and those optimal fluences are provided for us. If you look into your DCF, which is where your beam data is stored, there's a pre-configured data folder, and under that there's this portal dosimetry image prediction. In there, the optimal fluence patterns for importing to create this ADA for both the HDMLC and the standard MLC are available. And you can deliver that for all images. We should note that this ADA profile is simply just a set of zeros and ones on your fluence, optimal fluence. Anything not in purple is a 0 fluence, and anything in purple is a 1 fluence. We're going to calculate it onto a phantom, and then typically I'm going to use a 90 collimator. That's just my convention. That's what Varian's default is on their test plans, and we're going to make sure we note what the MU used are. You can calculate this to dose, and if you do, you're going to get different, obviously different monitor units per energy. I will typically calculate this with presets, and I'll just use 200 monitor units. But no matter what you do, you need to know how many are delivered. I'm going to take a second and just note something on the side. Anytime you want to image something, you need to make sure it's scheduled and integrated images are attached. Also, be sure that your imager vert is ready. If you use a verification plan, the imager vert is going to be set for you. But if you're delivering like these two types of plans are going to be, you need to make sure you set your imager vert to 0, or otherwise it's going to default to your default position, which is typically 50 for an MV image. Note that every kind of normal plan delivery rule applies. If you don't have a tolerance table, it won't be happy. If you don't have couch values, it isn't very happy and doesn't really deliver. And you'll be frustrated because you have to go back and reset all that stuff before you can deliver. So once we have those, we're going to jump right into kind of how we're going to model. So once we get the output factors, we're going to use the output factor tool that's provided in Portal Dosimetry. Conveniently, once you do that, you can copy those output factors to a clipboard and paste them in Notepad, and it's already in the MU tab folder. The next thing you're going to need is you're going to need the ADA file. So we're going to open it up in Portal Dosimetry again, go to the delivered image, and right-click on it, and you'll get an export to text file option. That exports, to a DXF file, and that DXF file is what we're going to use as our collected image to compare to our actual fluence to get a kernel. So put both of those in a location where you know where they are, because you're going to want to need to navigate to them, and then we'll jump into building the model. So when we get to the model, we're going to put a new beam data in. We're going to have a new add-on and add on the open field. The first thing I always do is I import my output factors. So right-click on the open field, input output factors, navigate to the place where you just put that. When you get that in there, you're going to want to interpolate your missing values. So if you didn't measure field size 1, 2, 3, 4, 5, all the way up to 40 by 40 and measure just a subset of those, you're going to need to interpolate everything in between. And then we're going to calibrate the dose rate. This is where I talked about when you calibrated your imager, you need to note the CU you selected, and that's what's going to go in here to the new output factor calibration. So if you calibrate it to 1, then 1 is what goes in there. If you calibrate it to 100, then 100 is what you would use. The next thing we're going to do is insert the intensity profile. Again, I find the best way to do this is just to copy the AAA generated intensity profile. So you'll right-click on the open field, you'll say Insert New, then you'll go up to the AAA algorithm, you'll select the intensity profile, go to Edit, copy the curve, and then go back to your PDIP and paste it in there. One mistake that's really easy to make is the distance from source defaults to 0.0. If you leave it in there, you'll end up with a broken kernel. So it'll be pretty obvious, but be sure that you set that distance from source. Typically in millimeters, that's going to be for a 6X, for example, somewhere in the ballpark of 1015. So 100 SSD plus 1.5 to Dmax. And I should note that intensity profile is in AAA is defined at Dmax. The last thing you need to do is import the actual fluence from the calculated data. to do this, you select the open field, but then you have to go up to File, Import, and then there's an actual fluence from database. That's going to bring up a patient explorer. You'll navigate to the patient that you have your plan in and then select the plan. From this, there should be no other fields in that plan. It should be just the ADA profile that you're looking for. So once you do that, that's going to pull that in. It's going to look like what we had before the actual fluence. And then the last thing is direct the model to the measured. So under portal image parameters, you're going to see a screen that looks like this. You have the option to put 2 images in. This is so you could put an image at 100 SSD, the calibration distance, and 140 SSD. You could do that from, the reason you would do that is it gives you a better SSD correction. However, in my experience, there's no reason except for using an AS500 or an AS1000. There's no reason to change your SSD. I do everything at 100. A couple things to note here, though, is I have this import portal image file from. This is the file path where I placed the DXF file that I exported. That could be different for anybody, but you can place that anywhere. You can't navigate here. You have to type that in. Be sure to put your collimator rotation in, and also, again, we made a note of the modern units. It's very important to get that number correct. I just wanted to show an example of a broken kernel. I think if you remember, I showed you earlier what a correct kernel will look like. Let me navigate back to it now. A correct kernel, remember, one more. Looks like this, very clean and exponentially decaying, and a broken kernel, again, looks like this. This kernel was broken because I did the output factors wrong, actually. I had the output factors set to, I didn't interpolate them. So I got a kernel that looked like this. You get something somewhat similar by not setting the SSD correctly. But either way, point being that if you do those steps wrong, most of the time you can see that the kernel does not give you that exponential decay, and you're going to want to go back and check those parameters that we put in. Another thing that could break this is if you were to use an actual fluence from, say, a 10x beam, but you imported a 6x measured ADA profile or ADA plan, that would also give you a kernel, and obviously that's going to break in a lot of different ways. So once we get the model done, we can jump on into verification. Varian provides some test plans they call QOpen, QMLC, QIMRT, and QRA. But what's most important about all this is IMRT commissioning is always going to follow a workflow. No matter what device you're using, you need to verify that you can measure output correctly, that you get good open field agreement, and after you do that with open fields, you can jump on to MLC transmission. I should note that you can't do dosimetric leaf gap without doing MLC transmission because you can't separate the two out. MLC transmission is the only one that you can separate away from dosimetric leaf gap. You can't do it the other way around. And then once we get the dosimetric leaf gap dialed in, we can move on to IMRT and RapidArc verification. So the two open test plans are large open MLCs with a small field and field movement. These have jaws that are fixed. The MLCs are open out past the jaws and don't attenuate the beam in any certain way. For example, you're going to get a 3x3 and a 10x10 and a 30x20, for example, a few asymmetrics. But the first thing I want to check on this is I always jump straight to the 10x10. And I want to see that my calibration and my prediction give me the same dose. If they don't, you can easily go into those output factors and scale that output factor from 1 to, say, a 0.998, for example. And in fact, I think my example had that in it. I'm sorry. Well, anyway, I think my example had 0.998 in it. And that shows that you're getting this, you know, this CU is reading 99.57 versus 99.86. You're getting really good agreement here. The next thing I'm going to do is I'm going to go in and I'm going to check that the open field profiles look correct. This is just an example of with that intensity profile in using a 38 by 38 field size. You can see under 2% 2 millimeter gamma, I'm getting a very poor analysis, and you can see that the predicted under the red and the measured under the blue in the bottom left corner deviate greatly as you get larger and larger. So what I do is I apply a correction to my intensity profile. That correction is used from these two images, and once I get that correction and apply it to my intensity profile, recalculate the model, this is what we get. What's really interesting is now we've got this full, really large field of view that's usable. For typical fields, for typical IMRT QAs, you know, prostate plans, for example, you may not see a difference in your IMRTs between the two intensity profiles used here and used here. However, maybe a large field pelvis using much more of the panel is going to give it a much different response if you were to use this intensity profile versus this one. So that's one of the major trip-ups that you can run into. Just need to be aware of it and be aware that you can change that intensity profile. You can play with it a little bit and come up with a solution here. Once I get these open fields done, I can move on to MLC parameters. I can move on to the transmission and the DLG. The most useful parameter, the most useful pattern for dialing these in is the chair pattern. If you haven't seen the chair pattern, you'll see an image of it here in a minute. It's named that because that's exactly what it looks like. And you can see specifically DLG and transmission out of it. But where do we start with those DLG and transmission measurements? Well, one place would be is we can measure them. Varian provides a measurement exercise. Transmission is measured by keeping the leaves stationary and taking measurements under the leaf bank. And DLG is a sweeping gap, and that's different thicknesses of a sweeping gap. You measure all of that with a farmer chamber. What's actually interesting here is you would think, okay, use a large chamber, we'll get volume averaging. Maybe if we use a small chamber, you'll get a better result, but that's actually exactly the opposite. We want to get some sort of average here. We need to be careful that we're not directly under a leaf or directly in between two leaves. That can dramatically change your response here. So using some small, super high resolution detector here is not necessarily the best case solution. But all that being said, whatever you measure there is just a starting point. We're going to tweak those based on the chair pattern. And honestly, we could probably even use another general starting point measured by other people. For example, Kerry Glidehurst and et al. Did some TrueBeam commissioning, and they published this data for 5 energies. You could easily start with these numbers from that paper, and again, dial it in specifically for your machine. I should note that each machine is a little bit different in my experience, but they're all pretty well in the same ballpark. Okay, so now we'll look at the chair pattern. In the upper right quadrant, where we're currently looking in our field of view down in the bottom left, those MLCs never move. So we can define MLC transmission there. This would be an example of a pretty decent looking MLC transmission. You can see that the predicted in yellow pretty well cuts through the middle of the measured in green. This is a really good example too of the resolution of the detector. You can see that each leaf and each intra-leaf leakage there in the transmission through those leaves, so you can really get a good example of how high the resolution of this detector is. So this would be an example of a good transmission used. As an example of how quickly it can change, I think I changed the transmission between this image and the next image by a couple tenths of a percent. I think I went from 1.25 to 1. And you notice that the transmission has dropped dramatically. It's not anymore following through the middle. I think I'm underestimating the transmission here, and this would have provided me with a better solution. The next step after we get transmission dialed in is to look at the DLG. The DLG is most usefully defined by the sweeping of leaves across an open space, which in the center of our chair is the best place we can see that. But overall, DLG is defined across the entire chair pattern. So anytime you get a decent agreement across there, and you can even see in the middle of the hump there in the bottom left, you see the predicted moving right through the measured image. That's an example of a good DLG. This is a really kind of an art. You can dial in the DLG really, really tight here. But we're going to get as close as we can with the chair pattern, and then we're going to look at the IMRT test plans, and we're going to see how useful, if our DLG is accurate or not. The other MLC test plan is we have the ADA pattern also in here. The ADA pattern is useful in a couple ways. It's not very useful in defining MLC parameters, but if your MLC parameters are wrong, it can show up here, but you can't really use this to dial them in any tighter. What's most useful about the ADA pattern is you can verify your kernel here. You can verify that the prediction is actually showing you what it should. It's predicting what is delivered. Once we get the DLG and transmission dialed in, we can move on to the RapidArc and IMRT test plans. These are provided by Varium. These MLC motions are always going to be the same on every machine. That's very important for me. I think that if we can pull out the optimization, then we can more accurately know information about the MLC. So I find these very, very useful because I'm not optimizing. I also find the IMRT plans much more useful than the RapidArc plans in evaluating the MLC because IMRT plans are field by field. The RapidArc plans are full arcs. It's the same concept as doing a plan IMRT QA evaluation versus a field-by-field IMRT QA evaluation. Plan evaluation can often hide errors by overlapping two errors together that cancel each other out, for example. RapidArc is very similar in concept, and therefore I find the IMRT plans much more useful. And these are sweeping arcs, or sweeping, sliding window IMRT plans. And these leaf motions are representative of some sort of treatment. A few of these are harder to pass than others, but they're all very useful in evaluating your MLCs. So I'm going to deliver these as portal test plans, verification plans, and then we're going to evaluate them. This image right here is one of those test fields, and this is an example of a good DLG. You can see that the predicted yellow line is really running pretty much through or above and below the green delivered. As an example, the next image here is an example of a DLG that was too high. I've switched back and forth between them, and you can really see the difference where the predicted image, the predicted profile is moving above the delivered, but these are the same delivered test plans. So as an example of a DLG when you're too high, maybe we need to go back to the chair pattern if we saw this and say, can we make it a little bit better? And then again, this is an IMRT or a RapidArc test image showing that the delivery is excellent. So just a few things that wraps up the portal dosimetry commissioning and dialing in the MLC and MLC transmission and DLG, but just be aware that portal dosimetry is never a verification of a dose calculation algorithm. Portal dosimetry is an independent algorithm, and it is simply testing the machine's ability to deliver the plan. You will notice things like if your output on your machine is too high, for example, or if you overmodulate, you will see those, but it is not a dose calculation verification. The advantage of this is, advantage of portable dosimetry is that you're never going to have heterogeneity issues. For example, using a matrix or a map check from IBA and Sun Nuclear respectively, you may need to calculate onto a water phantom and then extract an effective depth profile, or if you take a scan of those, you have to account for the fact that the diodes throw artifacts. You never have that problem here. And then the other advantage is if you do perchance have some issue with the dose calculation algorithm, you're never going to see that in QA. That being said, that means that your calculation algorithms probably need to be checked more periodically. You need to be doing a quarterly test on delivery to an ion chamber or to a different array or something like that to more stringently check your TPS. I want to reiterate that the machine beam profile calibration, once you set your portable dosimetry algorithm, never needs to be changed. It should always be the same. The intensity profile that you're using in PDIP is dependent on the profile correction that you put onto the panel. The other thing that I want to talk about is how often do we need to calibrate the dose on the panel? You should only ever do it as needed. For the older panels, it was more frequent. I would probably spot check it on a monthly basis whenever I did my monthly calibration output check. But for the newer panels, for the AS1200 on my machine, it's so tight that I, in fact, use it as another form of daily machine output verification. As I see my portable dosimetries start to drift, I often can go in and check my output with a chamber and see that my output is starting to drift as well. So for the newer panel, I personally, I spot check that annually when I do a TG51. But you should also remember that calibration, again, is relative to the output of the machine. If you're going to calibrate this monthly, for example, and your machine starts to drift to, say, 1.02, then 1 point, et cetera, then your calibration of your panel will drift correspondingly. So just be aware of that. So in conclusion of all of this, no matter what IMRT QA commissioning or IMRT commissioning you're doing, it's important to really follow your process, follow the verify your output, verify your open fields, then move on to transmission, then DLG, and then you can actually start delivering test plans. You know, not only to validate your device, but also to validate all the parameters using in the MLC and your output, for example. But if done correctly, portable dosimetry is a great tool to do patient-specific QA. It's great to use for physics, and as a device for the clinic, it's excellent. I appreciate it. Go ahead, Karen.
Well, thank you, Bryce, for a great presentation.